here we have a little block that sits on that surface. And, well, what can one do with a block? You can push it or you can pull it. And that's exactly what we're going to look at now. So I can exert a pushing force onto this block here, F push. But I could also pull it like this, F pull. And the question is, how can we formalize this a little bit more? We can now also look at a small piece of rope or a string. And, I could, in a tug of war, I'm going to pull here. And I'm also going to pull here. And we'll see who's going to win. So we have two pulling forces here on either side. In a slightly different scenario where we're going to put both of these things together, we have a block here sitting on a surface, and we have a little string attached to it. And let's say we have a pulley here, and the string goes around there, and there's a little mass hanging here. We want to now describe what this force is here that's pulling things. And for that, we have to look at what's going on in that little string. So let's draw another string. And this is our string. And let's take an imaginary cut right through the middle here. And I'm going to draw both pieces here. This is the left part, and here is the right part. And what's happening in this rope here now? Well, there is a force acting on the left object due to the interaction with the right one. And here we have a force on the right one due to the interaction with the left piece. And that, of course, happens anywhere, I take a cut here along the line. And we can even formalize that a little bit more by just placing our coordinate system here. And let's say x equals 0 here. And so for all x along this line, we always have these pairs of forces. So there are an interaction pair. And if I look at the rope from afar, they will cancel out. But if I look at what's going on inside the rope, then this is what they are. And we know from Newton's third law that FRL equals minus FLR. So they're forces of the same magnitude, but the opposite direction. If they weren't the same, then my rope would get in trouble. But what we want to define now actually is tension, the tension force that is that's happening along this rope here in our tug of war if someone pulls from the outside. And for that, we're first going to look at the magnitude of our interaction pair here, FRL. And that, of course, equals the magnitude of FLR. And we're actually going to define now this magnitude here as the tension force. And that is true for all x along this line here, that we have this, the magnitude, that this is the magnitude of this force here. And from now on, we're going to call, or when we talk about tension in a rope, then we talk about the magnitude of one of these internal forces here.
Today we'd like to discuss tension in a rope. Under what conditions is the tension uniform? Recall that if we had a rope and say we were pulling, here's our one end, we'll call that, we're pulling at this end with the force A, and we pull on this end B with the force B, that what we meant by tension at any point in the rope was that we took an imaginary slice of the rope P and we looked at the two sides. And here, if we call this the left side and this the right side, then on the left side, we have that the right side of the rope is pulling the left side of the rope by some force F. And this is the left side. and the right side is being pulled by the left side. So that's the right side being pulled by the left side. And what we defined the tension at the point P was to be the magnitude of this action-reaction pair. And that's how we define tension at a point inside a rope. Now we'd like to address the question is, when is the tension, under what conditions can we say that the tension is uniform, which means that at all points P, the tension is the same. And in order to analyze this, we'll apply Newton's second law. So let's begin with the same situation as before. Let's consider a rope where we're pulling this side with a force at the end. By the way, we can call this the tension at that end, T of A. And on this side, we can refer to this as the tension on side B. Now, suppose that our mass of the rope is non-zero. And we now want to apply Newton's second law. But let's also apply the condition that the acceleration of the rope is non-zero. So you're holding the rope under some tension by pulling both sides, but the rope is not accelerating. And so what does that mean when we apply Newton's second law to the rope? Well, let's just arbitrarily call that our positive direction. We see by vector decomposition that we have TB minus TA equals mass of the rope. But because the acceleration of the rope is 0, this side is 0, and we can use Newton's second law to conclude that the tension in the rope is uniform when the rope is not accelerating. And this is what we'll call our case 1, A0, tension in the rope is uniform. Now let's suppose, case 2, that A is not 0. And so now we have the rope. This is point B. Here's point A. We'll choose a uniform direction, A. And now we can see, when we apply F equals ma, that TB minus TA equals mass of the rope times the acceleration of the rope. So you're pulling such that TB is greater than TA by precisely the quantity mr times A. And so the tension at the ends are not the same, and therefore the tension in the rope is not uniform. Now there's a special case here that we want to consider. So even though A is non-zero, let's assume that the mass of the rope is very small. And this is often, people call this, assume the rope is massless. Well, that's a little strange. We can say the very, very light string is often the same type of modeling. And under those circumstances, with that assumption, you see that there is no contribution here. And with that assumption, that the tension is approximately uniform. Ropes are not massless. There's a small difference. But under those circumstances, when we say a very light rope, that even if it is accelerating, implies that T is uniform in the rope. And we can say the rope is under uniform tension. And we will often refer to this case when we analyze problems where we're pulling objects, for instance, in a typical pulley problem. One of our classic problems to analyze using Newton's second law is the motion of two blocks with a rope that's wrapped around a pulley. So imagine we have a pulley P, and we hang from that block 1, and we hang from that block 2. The pulley is suspended by another rope, and it's attached to a wall. And let's now try to use Newton's second law to analyze this motion. Now, going back to our methodology, the first thing we want to ask ourselves is to identify what are all the moving pieces. So I'm going to make my first assumption here that the rope pulley surface, so that's right here, is frictionless. Now what that assumption means is that the pulley will remain at rest. And therefore, when we want to break this problem down, our first question is to identify all the moving objects. And so we really have three. We have mass, which we labeled by 1, 2, and the rope. So our goal now is to identify all the moving objects and to draw free body force diagrams for each moving object. Now, one of the things that I'm especially interested in talking about is to keep in mind to identify action-reaction pairs. So as I go through and draw these free body diagrams, we want to ask ourselves, what forces form Newton's third law action-reaction pairs? So what I'll do is I'll start with object 1. Now, object 1 has a gravitational force, m1g, and the rope is pulling object 1 up with the tension at the end of the rope, T rope 1. So the action-reaction pair to m1g is the Earth, is the force of this mass on the Earth, which we're not considering. What about the rope? So now let's draw a picture of our rope. And mass, this object here, is pulling the rope down. And so we have on the rope object 1 pulling it down, and this is our action-reaction pair. What are the other forces on the rope? Well, over here, object 2, T2, is pulling the rope down with the tension at the end of that rope. Now, also, the pulley is exerting a force on the rope upwards because we have that force. And so these are the force diagrams on the rope. Now, what about the action-reaction pair to T2 rope? Well, let's continue and draw 2. We have, again, gravitational force on 2. The Earth is the action-reaction pair. The force of 2 on the Earth upwards is equal to m2g of the Earth downwards. We're not drawing the Earth in this picture, so we don't show it. Now, here is the force of the rope on 2, and there is our other action-reaction pair. So these are the Newton third law pairs in this object. Now that we've identified all the forces, we want to apply Newton's second law to each of these objects that are moving. So let's begin by remembering that if our next assumption here, it's assume that the mass of the rope is very light, and then the tension in the rope is constant, and the implication of that is T2r equals T1r. And that's why we can now identify this as T and that as T. A little bit later on, when we talk about pulleys that have mass with friction between them, the tension on the two sides of the pulley will not be the same. But for the moment, we've made these assumptions, and that holds. And now we just really have objects 1 and object 2 to analyze. And so one of the things that helps a lot is we need to choose unit vectors in order to write down the vector equations for Newton's second law. So let's just here assume for ourselves that m1 is greater than m2. This gives us some feeling for how the system moves. I like to do this because it gives me a way to choose my unit vectors to make all the accelerations positive. So when m1 is bigger than m2, I expect m1 to go down and 2 to go up. And that's how I'm going to choose unit vectors, j hat 1. Now, here is the very interesting thing. We choose a separate coordinate system for each object. So I'm going to write that down. We want to choose separate unit vectors for each object. And our accelerations will be with respect to those unit vectors. This is where a lot of people get tripped up. So here, I'm choosing j hat 2. And when I choose that, I expect a2 to be positive because 2 is going up in the direction of j hat. And here, I expect a1 to be positive also because 1 is going down. Now I can draw Newton's second law on 1. So I have F1 equals m1a1. And now I analyze my forces. m1g is in the positive j hat direction. T is in the negative j hat direction. So I have m1g minus t equals m1a1, which I'm expecting to be positive. And in the same way, on 2, F2 equals m2a2. I look at my force diagram. Now notice, j hat is up, so t is positive. m2g is minus my direction. m2g equals m2a2. So I now have two equations. But when I look at these equations, I see that I have three unknowns. I have t, a1, and a2. But I have a constraint. Because these objects are moving together, and the way I've chosen the coordinate systems, a1 is equal to plus a2. Both are positive with respect to my choice of coordinate systems. And so these two a's are the same. And now I can solve my equations for t and a. And let's quickly do that. m1g minus t equals m1a. And over here, let's solve for the tension. For the accelerations here, t is equal to m2a plus m2g. And when I substitute the t into that equation, we'll find some space for that. We'll write that as, if I put in the m2 minus m2a minus m2g, and bring the m2a to the other side, then it's a little bit of algebra, but I think you'll trust me that this is m1 minus m2g over m1 plus m2. Now, we're almost done. We need to check our answers. First off, does it have the dimensions of acceleration? Answer, yes. Mass divided by mass. G has the dimensions of acceleration. So that's my first check always with my algebra. Second check, what if m1 is equal to m2? Then the acceleration is 0. I expect them to be balanced. I've said that m1 is greater than m2, positive sign. My a is positive. That's how I set up my coordinate system, so I expect that too. By the way, our symbol a was equal to those. And so I'm pretty confident that my result is correct. And that's how we apply Newton's second law to the pulley with several assumptions: frictionless surface, massless rope, and think about how we chose our unit vectors. Each object gets its separate coordinate system. I'm not using the same coordinate system for each object. I could have, but then there would be a subtlety to this condition. The accelerations would be opposite in sign. We now would like to analyze the force law on an idealized spring, a force law called Hooke's law. Let's begin by drawing an ideal spring connected to an object on a frictionless surface. So we'll draw our object. We'll draw our idealized spring. This surface here is going to be frictionless. And this is a wall, and we'll draw it like that. And now what we'd like to do is to introduce the force law for a spring, a force law which will be called Hooke's law. So the way we'd like to analyze this is by drawing two pictures. Our first picture will have the spring at an equilibrium picture. So let's draw the wall again. And let's draw the spring and our object. And This is called the equilibrium picture. So I'll write equilibrium picture. And now what we'd like to do is draw a picture, a dynamic picture at some arbitrary time t. So here we have a dynamic picture at time t, and I'll draw it in a second. So we draw the same object, and now we're going to move our object to some arbitrary position. In this case, the spring has been stretched. Wall, frictionless surface. And now I'm in position to choose a coordinate system. So what I'll do is I'll choose my origin at the edge right here. This is called x equals 0. I'll show it in the dynamic picture. And my coordinate function for the object here, I'm going to refer to that as x of t. Now notice that this coordinate function is also an indication of how much the spring has been displaced. As far as directions go, we'll have an axis. And this is our plus x direction. So usually we indicate that with a unit vector I hat. And now Hooke's law is the statement that the force on the spring, that the force on the object, F, is proportional to how much the object has displaced, which represents either the stretching or the compressing of the spring. So it's equal to minus kx I hat. Now, what does this minus sign mean? Well, this is an example of what we call a restoring force. And let's look at a couple of examples. When x is positive, that means that the object has been pulled out from the equilibrium position. The spring is undergoing tension. It's being stretched apart. The molecules in the spring that constitute the spring are being pulled apart. And there's a restoring force inside the spring. This is an atomic force in nature that's pulling the spring backwards, hence exerting a restoring force on the object. So this force is in the minus I hat direction. It's restoring in that direction. I'll draw the force like that. Now, suppose we drew another picture where the spring has, the object is pushed in, compressing the spring. So let's draw, once again, a diagram. And let's show the spring under compression from our equilibrium position. Now here we have, again, that x of t. But in this case, x of t is negative. And so this is extension. So we'll call that case A. And case B, when x is less than 0, it's under compression. And then we see that with x negative and the additional minus sign, the force is in the positive direction. And so in both instances, the force is a restoring force back to equilibrium. So the restoring force, whether you're under extension or compression, is always pointing, let's call it, is the direction of the force is towards the equilibrium position. And this example of a restoring force is also only proportional to x. And so in that case, we can add the word linear, because it's just to the single power x. And this is an example of a linear restoring force. And this is a model for an ideal spring. Now, this constant k is called the spring constant. And the units of the spring constant, if you divide the units of force by the units of distance, so we have SI units are Newton over meters. And that's the measure of the spring constant.